Snakes on a Plane, now in 3D. And for us, it's calculus, now in 3D. This video serves as an introduction to section 14.1 on the topic of functions of several variables. Now, many quantities depend on more than one variable. For example, if we want to compute the volume of a cylinder, that volume depends both on the radius of the base of the cylinder as well as the height of the cylinder. To compute the area of a triangle, we need to know the lengths of both the base and the height. Our notation for a function of two variables will often look like this: z equals f of xy. Now, notice that the x and y here are our independent variables, while z is the dependent variable. The domain is a subset of R2, since the domain are all values of x and y that we can plug into our function and everything still makes sense. The range is a subset of R. It's all of those output values, the possible z values we can get. Let's do some examples. Let's evaluate various functions at the point 4, 5 and find the domain. Starting with the function f of xy equals the square root of x plus y divided by x minus 3. To evaluate this function at the point 4, 5, we will simply replace every x with the number 4 and every variable y with the number 5. So we'll have the square root of 4 plus 5 divided by 4 minus 3. This will give us the square root of 9, or 3, divided by 1. So f of 4, 5 is 3. To find the domain, let's quickly review some basic domain rules that were true in single variable calculus and still hold. If z is an even root, such as a square root of a function f, then that f must be bigger than or equal to 0. Another way to say this is that we're never allowed to take the square root of a negative. If z is a quotient, f divided by g, then g is not allowed to be 0, or we're never allowed to divide by 0. Finally, if z is a log of f, then f must be strictly positive. So when we look at our function, we see there are going to be two domain rules coming into play. We have a square root and we have a quotient. Let's focus on the square root first. So we first see that the domain must satisfy that the quantity under the square root, x plus y, must be greater than or equal to 0. Solving for y, this tells us that y must be greater than or equal to negative x. We also must deal with the fact that we have a quotient. We can't divide by 0, and so in this example that tells us that x is not allowed to equal 3. So our domain of the function is that y must be greater than or equal to minus x, and x is not allowed to be 3. To sketch the domain, keeping in mind the domain is a subset of R2, it would look like this. So we have the line y equals minus x. Notice that y must be greater than or equal to minus x, but we've excluded the value x equals 3. Let's do another one. Let's evaluate the function natural log of x squared plus y minus 1 at 4, 5 and find the domain. To evaluate again, we'll replace the value of x with 4 and the value y with 5. So we get the natural log of 16 plus 5 minus 1, or the natural log of 20. For our domain, recall that whatever we take the natural log of must be strictly positive. So x squared plus y minus 1 must be greater than 0. Solving for y, we see that y must be greater than 1 minus x squared. So to sketch our domain, we'll want to think about the parabola 1 minus x squared. So there's our parabola. Notice we have a dotted line representing the parabola, since our domain says that y must be strictly greater than 1 minus x squared, and we've shaded in the region greater than 1 minus x squared. So here's a picture of the domain. One last domain example. Suppose f is the function square root of x plus square root of y. We have two square roots. They both must be independently happy. So x must be greater than or equal to 0, and y must be greater than or equal to 0. Think about your xy plane. Where will we shade so that x is greater than or equal to 0 and y is greater than or equal to 0? Well, that will be our first quadrant. So here's a picture of the domain of the function in example C. Great, here's a different one. The wave heights h in the open sea depend on the speed v of the wind and the length of time t that the wind has been blowing at that speed. Values of the function h equals f of vt are recorded in feet in the following table. So here we see the values of our function as recorded in the table. So the heights of the wave are dependent upon both the wind speed v and the amount of time the wind has been blowing at that speed t. Let's answer some questions about this function. First of all, what is the value of f of 4015 and what is its meaning? So here we see that the wind speed v is 40 and the amount of time the wind has been blowing t is 15. Looking at the chart, we see that f of 4015 is 25, which means that if a 40 knot wind has been blowing for 15 hours, the wave heights will be 25 feet. Great. What is the meaning of the function h equals f of 30t? So here, the function f of 30t is the wave heights if a 30 knot wind blows for t hours. Notice that the function here is increasing, but increasing at a declining rate as t increases, with a maximum value of approximately 19 feet. Let's compare that to the last example. What is the meaning of the function h equals f of v 30? Well, the function f of v 30 is the wave heights if the wind blows at v knots for 30 hours. The function is increasing with no apparent limiting value since the values are just getting larger and larger and larger. Now, a new definition. The graph of an equation z equals f of xy is called a surface. So let's find the domain and sketch the graph of z equals the square root of 16 minus y squared minus x squared. Because we have a square root, for the domain, we see that the quantity under the square root, 16 minus y squared minus x squared, must be greater than or equal to 0. We can rearrange this equation to say that 16 must be greater than or equal to y squared plus x squared. Now, x squared plus y squared equals 16 represents a circle centered at the origin of radius 4. And we want our radius to be less than or equal. So a picture of the domain will have that circle, x squared plus y squared equals 4, and we want our quantities to be inside of that circle. How about for the surface? For the surface, note that because z is the positive square root of 16 minus y squared minus x squared, then z must be greater than or equal to 0. And if we square both sides of this equation, we get that z squared is 16 minus y squared minus x squared. We can rearrange this equation to make it look like something that's a little more familiar to us. Here, we have the equation of a sphere centered at the origin with radius 4. But now keep in mind, for the entire surface, we don't get the entire sphere because recall that z had to be greater than or equal to 0. And therefore, we get the top half of this sphere. So if we wanted to sketch the graph, we would sketch the top half of a sphere centered at the origin of radius 4. Great. That's all for this introduction. Thanks, guys. Bye.